it's all downhill from now. I can only disappoint. I have on occasion run colloquium or seminars out to an hour and a half or 15 minutes, but I'm trying very hard not to end on time. Anyway, so this is going to be a hodgepodge lecture, and I hope I can control myself and talk slowly enough about what is going on. So let me talk about some of the challenges. I'm sure you all know the data, but just to remind you, from 1850 to 2000, and this is now 2024, the end of 2024, the temperature global mean average is increasing. The UN target of 1.5, we're in the process of passing. This year, we went above it, it'll go down a little bit, but it's going to go up. So that's where we are now. Because of the temperature, many people are beginning to notice the weather has been changing, especially over the last decade or so. But I want to remind you, if you may not know, that the full effects of the greenhouse gas we've already added to the atmosphere won't be reached in at least 100 years. And the reason it won't be reached in at least 100 years is we now have floats around every roughly 1 degree around the world, Argo floats. They go up and down from the surface, first generation down to 2 kilometers, the next generation down to the bottom, which can be as, average 3.7 kilometers. 90% of the heat is in the deep ocean. The weather is determined by the land and ocean surface temperatures. And so, because it's like a glass of ice cubes, if you've got a big heat sink, the heat can go in, but the glass stays cool until you warm up the reservoir. This reservoir is very big, the mixing is very slow. We now have measurements of the mixing, so this is not a climate model. These are now measurements. And so, that's a real issue. I liken it analogous to say you were smoking from the time you were 20 until the time you're 40, and then you realize this is bad for you, but you set in process a lot of things that eventually, even though you might have stopped, and it happened to a friend of mine, for 30 years, she died of lung cancer at age 80, because it caught up. Now the good news is, as far as we know, if you reverse the temperature, a lot of this stuff can be reversed. But we have to reverse the temperature. Holding steady is not good enough. Because we set in motion things like glaciers, that once the plastic deformation starts, it doesn't stop until you restore what's called the grounding line. This is the ice above the land, off land that supplies the friction. Okay, now there's a correlation to the rising temperature in climate models. You probably have all seen things like this, and if you take out human emissions, this is what you can simulate, and this is observed, and it looks very convincing. And so it's showing that it's consistent, but the climate models are actually have to be still, despite many decades, still have to be hand-tuned. Because they will go unstable. And they also cannot really predict precipitation in any way whatsoever, let alone storms or hurricanes or tornadoes. Even rainfall precipitation over a long period of time doesn't work. And so that's what we have. And so I'm a big believer in statistical data. And the more statistical data we have, the better. There's emerging statistical data that says the water-climate linkage seems to be increasing in volatility. So this is no more climate models, because the climate models do have large uncertainties, but just statistics. And you can go from very dry to very wet. You can go hot and cold. I see this in California, and the big LA fires was exactly that. You had a very, very wet year, lots of wheat growth, because not much grows in LA area, followed by extremely dry year. And it was a tinderbox condition. And so we're going to expect more of this volatility. And then this is statistics, this is not models. Okay, so where are we and where were our goals? Where are our goals, the world goals? So on the x-axis over here, you see time from 1990 to 2100. Let me just say on the outset, the worst is not in this century. It's in the next couple of centuries. Again, because of the long time delay. On the y-axis is the amount annual global greenhouse gas emissions in billions of tons. 50 gigatons is not just carbon dioxide, which is a little over 42 gigabillion tons a year, but it also includes all the other greenhouse gases, methane, nitrous oxide, and refrigerants. So where are we? Well, we're kind of here. There was a little downturn in the world economy because of COVID, but it's bounced back. And we're somewhere between current policy pledges. These are pledges made by, let's say, the Conference on Parties, the COP conferences. And if you believe climate models, taken with a grain of salt, so mentally just make the error bars a little bit bigger. It doesn't really matter, but we're heading towards about 3 degrees, a little bit over 3 degrees. This is business as usual, nothing. To get to 2 degrees, 1.5 we're passing now, in the next year or two for sure. To get to 2 degrees, you have to go to zero emissions in everything around the world due to humans. And so that is unlikely. So my best guess is we're gonna be around 3.5 degrees. Don't really know, it's a wild guess, but it mostly depends on climate models. Now the World Bank has predicted 200, maybe 250 climate refugees by 2050. So what's a climate refugee? If a weather pattern changes for a year or two, that's all it takes, the local agriculture collapses, the farmers lose their farm. The world food production, because in the macroeconomic sense, is not under threat. It's just the local area. And now most of these 200 plus refugees are within continents. But as things get desperate, we see that they have nothing to lose. You watch refugees going over the Darien Gap between Colombia and Panama, you know, trying to get on rubber boats to England. And so you see a lot of people, even though they know there may be a non-negligible chance of dying, let alone getting rearrested and sent back, things can get very desperate. And we also know that even 10 million refugees in Europe and the United States has completely transformed the politics of the world. It's a quick anecdote. When I was Secretary of Energy, we knew that as sea level rises, Bangladesh is very low-lying and then mountainous, very poor people. So the Indian ministers I was talking to were saying, oh, you know, this is going to be tragic. A mostly Muslim country, they're very poor, they're going to get desperate, they're going to come over here, we don't know what to do. Do we shoot them at the border? They asked in semi-jest, but desperate, we don't know what to do. And so we have the climate refugee problem, which should not be underestimated, because when local societies and law and order collapse, and we've seen this due to, you know, you go to mobs, gangsters, and stuff like that, and you don't get to a government, you don't go to a government that's responsible for citizens. It becomes something else. Okay, so now, if we want to limit greenhouse gases, this is where you have to ask where it's coming from, and this is an IPC summary for policymakers, agriculture, heat, electricity, industry, transportation. So what does this mean? This means not only do you want all your electricity to be carbon-free, you want to get rid of all the emissions from steel, concrete, chemicals, plastics, textiles, and all forms of transportation. Means you have to get the entire food supply chain, which is roughly 20-25% of greenhouse gas emissions. You have to stop carbon emission in that. And at present, I'll talk about it later, we have no solution for this. Because the greenhouse gas emissions, a large fraction of it comes from use of fertilizer, and we're 8.2 billion going to 10, maybe 11 billion before tapering off. And as the developing countries have more wealth, they want to eat better food. Unfortunately, they seem to also want to follow the American example of eating more meat, but never mind that. Food production is an unsolved problem. Okay, now study of the history is important, and there's this old guy telling a young scholar, those who don't study history are doomed to repeat it, yet those who do study history are doomed to stand by helplessly while everyone else repeats it. I kind of feel that way. And so a little bit of history. First, let me say that if you look at the progress of the world, the several industrial revolutions, the few agricultural revolutions we've had, new materials has been a significant driver. So very quickly, James Watt didn't invent the steam engine, he improved the steam engine, and then you have this transition from horse and human power to horsepower. So instead of horses dragging things, you have iron horses. Okay, so that started it. There was another big innovation. It was an innovation of, didn't invent steel. Bessemer didn't. Steel has been around for thousands of years, but it was not commercially produced in any way whatsoever. And so what happened was during a war, the explosives, the chemical explosives got more and more powerful, and the cast iron cannons would then explode. So they wanted something stronger. The war was the Crimean War. What was the Crimean War? Well, it was Russia invading Crimea and France and England saying, we don't want to do this. Sounds familiar. But it led to the Bessemer process of steel that made steel mass produced. Okay, so let me, a few other examples. I worked at Bell Labs for 9 years. We all know that Bell Labs invented the laser and the transistor and the field effect transistor and information theory and all these other things. And so John Bardeen and Walter Bertin made the first transistor. Shockley was not on the first transistor patent because he didn't have anything to do with it, but he was their department head and he got really mad. And he called them both in his office and said, you know, sometimes the people who did the work aren't going to get the credit. I'm going to get the credit for this. So what he did, though, is he was a brilliant theoretical physicist, and he knew quantum mechanics well. So he went to a conference, holed himself in a room in a hotel for 2 or 3 days, and developed the quantum mechanical physics of semiconductors. So he deserves to be on the Nobel Prize. He was really irked. But he was so mad that Bertin said, I can't believe he's not, or transferring out, I don't care. Even though I'd like to work with transistor, I'd like to work with this thing. Bardeen has the same feeling. He says, I'm not going to work on the transistor, even though it's used. I got to find something else. So he worked on superconductivity. Okay, so, but what you don't know is that this would not have become practical unless we found a way of purifying semiconductors, starting with germanium and then silicon, to a high enough purity so you can intentionally dope. And it was the zone refining Bill Fan invented that actually made it reality. And so for that reason, he's revered. When I first joined Bell Labs, I was in this distant wing, and this old guy going to come out, and he comes in for a couple hours, and he goes, totters out. Finally, I asked my department, who's this guy? And he says, you don't know him? I said, no, who's this? Bill Fan. I said, yeah, what do you do? He said, oh my God. He said, he invented zone refining. Without zone refining, we wouldn't have the transistor. And he says, you remind me of these 2 young cavemen. And they watch this old guy go around, and one guy says, oh, you know who he is? No, who's he? He's the guy who invented the wheel. And the other guy says, what did he do lately? Also, we borrowing from seed crystal immersion. Thiel and Sparks, also at Bell Labs, invented the pulling of single codes. So it's these inventions that actually made it possible. You know the Nobel Prize for fiber optics communication by Charles Kao, but it wasn't that made it a reality. It was first Corning, and then Corning and Bell Labs made it so pure and so good that the losses became essentially now dominated. Oh, it's dominated by inhomogeneous scattering of the cooling of the glass. That made it a reality. And if you can figure out how to make glass to cool a little bit lower temperature, you decrease the scattering a little bit, it will make it a little bit better. But it's good enough now. And then of course silicon photovoltaic cells, also invented by Bell Labs, constant technology. So these are all materials that gave us the communications revolution, the computer revolution, you name it. New materials are popping up. Great hope in these so-called perovskite materials. They are made at much lower temperatures, much less investment. There's thin films that can put on substrates. Everything's going for it. The tandem silicon plus perovskites now are 35% efficiency, and this is great. The only downside, not solved problem, is the durability remains a challenge. They got to last. The economist types, business types think 20 years is old. You don't need 30 or 35 years the way silicon is today. Silicon actually was deployed at 20 years. So this is something. Okay, so new materials, a big deal. Since I'm talking about materials, let's step really far back and talk about what are the materials we use in the earth today. And it comes in two categories. This is on a log scale of the amount of metric tons used. Oil, coal, natural gas, number one. Concrete, okay? Wood materials, trees for asphalt, cement. Then a little bit further down, steel. And then you've got to drop by almost 2 orders of magnitude before you get to the next most abundant stuff in the Earth's crust. Production, not abundant in the Earth's crust, is aluminum. This blue stuff are plastics, so the feedstock of plastics is fossil fuel. So what we drag out of the Earth is mostly fossil fuel and rock. So that's something, that's the fossil fuel stuff. If you look at this, we're probably going to face a copper shortage, maybe not for 100 years, maybe not for 200. And shortage, you have to qualify to what shortage means. Shortage means the price doubles or triples because it's just supply and demand. And so the question is, when will that happen? And you can't make economic predictions beyond 20 or 30 years anyway. And also, but you can make estimates of resources. And then what you're doing is you're going to lower and lower grade ores. So that's something one has to think about. But remember, since most of the stuff we drag out of the ground is in the form of carbon, and this is a challenge to chemists and physicists and material scientists, that if you can, there's an existence proof, you can make carbon conductors in terms of conductivity to weight are better than copper. But there's an unlimited supply of carbon, and it's not going to go in the atmosphere. And you can maybe use carbon instead of steel for reinforced concrete and things like that. And so the question is, how do you do this? The existence proof is in nanotubes, in graphene and things like that. Very, very good conductors, but it's nowhere near practical. So something, if you're looking about something to think about in the coming decade, this is certainly a big deal. We're going to need a fourth industrial revolution. And then you've all heard that the levelized costs in the United States of wind and solar are now below that of natural gas, and which is some of the cheapest in the world, all true. But the full cost, we're in California, we're 60% renewable, carbon-free energy, renewable energy, and 10% nuclear. We're going to go higher. We're going to go probably to 80 or maybe higher. But as you get higher and higher and higher, you're running into issues and problems. And you need enhanced transmission distribution. You need backup generation, preventing energy storage. So the full cost of renewables, it has to be included in this stuff once you go over 30%. And by 50%, it becomes significant. By 80%, it's huge. And so, roughly speaking, a factor or two cheaper is about what you need because of all the other stuff. But it also depends on the cost of the other stuff. Okay, so long-term energy storage is crucial, absolutely crucial. Let me show you a picture of my favorite battery. Let me explain how it works. When the wind is blowing or the sun is shining, you pump irrigation water into a tower. When you need the water, you open up the valve. That's not very energy intensive. And so pumped storage, if you have a dam and then you have something down below, a little holding pond, and you pump water up and then let it come down, if it's 100 feet or more, it's 75% efficient. If you're a couple hundred feet, it gets to be over 80% efficient round trip, excluding evaporation loss. It's pretty good. It's actually as good as some batteries being considered. So that's a big deal. I should also say that one of the things we do need, and it is emerging, is we need utility scale storage that so that you can use ambient air to cool. That's very important. Ambient air cooling means the battery has to be operable at 50, maybe even 60 degrees centigrade. If you have a battery that's operable at 60 degrees centigrade, at least for the first half of the century, we won't need to go higher. Maybe next century, so these now exist. I hunted around Google, I found an American supplier. It's a sodium battery, it's megawatt scale, and then I looked at what and of course China's doing this as well. And so once you have this, not refrigeration, hot temperatures, then sub-Saharan Africa, South Asia, Mexico, everybody opens up. Okay, right now our batteries need refrigeration. If you take your electric vehicle and park in Phoenix Airport, the battery overheats. It uses the battery to cool itself, and after 4 days, the battery is dead, not retrievable, dead. Okay, so this is a very big deal. Now, conventional batteries are also making great progress. In this graph, I'm talking on the x-axis, the energy per unit weight, watt-hours per kilogram. On the y-axis is energy per unit volume. This is the Tesla battery. I think in 4 or 5 years, maybe sooner, we will be up here, as is a little out of date because I'm on the board of a battery company and we're shipping batteries at 500, 550 watt-hours per kilogram. The biggest customers are, this is maybe the only American battery that may survive China, but maybe not. The biggest suppliers are for drones. The next biggest is actually we have a market in China for those very lightweight motor scooters that you can pick up and put into your apartment, don't leave it on the street, is another thing, okay? Battery costs have really started to plunge, especially after you go to wide-scale deployment. On the x-axis is the number of deployed battery storage. Every tick mark is a power of 10. On the y-axis is cost, but on a logarithmic scale. So this is an example of what you call a learning curve. Per unit of stuff you've made, the cost comes down by a certain fraction. Let's say 10%. Just make up a number. You double it, another 10%, or go up another 10, another. So it goes down exponentially. So hence on a log curve, it's a straight line. And so the cost of batteries in 2000 were $2,000 a kilowatt hour. 2020, they're $100 a kilowatt hour. That's what the OEMs will pay for beginning to be a battery system. By 2030, maybe $50 a kilowatt hour for EV batteries. Utility scale batteries are more expensive, maybe twofold more expensive, because you want them to work for 30 years, not 10 or 15 years, and they have to be much more reliable. You know, if your battery fails and your Tesla stalls, that's okay. Blackout, not okay. What stops learning curves? Well, a couple of things, but one thing for sure that stops learning curves are material shortages. And so, in addition to copper, cobalt and nickel are already being priced out of EV batteries. It's too expensive, even though the energy density is lower, but now people are working on trying to make metal lithium anodes so it will be even higher. Rare earths the mining is very energy intensive. It uses high acids. It's very polluting. And so to get a non-polluting rare earth refining is a true deal. Then you want to separate the rare earths. So that's a chemistry problem. How do you get cheap separation of rare earths? And how do you get the thorium and uranium out of there as well? Because it usually comes So these are materials questions, problems that are sitting out there waiting to be done. But having said that, the EV batteries are going great guns. I've shown two cars. One is a Tesla Model 3, long range. It's the only one you can buy now in California, and this is the list price on the website. This is the range. It's got fabulous acceleration, 0 to 60 in 4.9 seconds. And the battery chemistry is such that in 15 minutes, at 240 kilowatt power, in the middle of the battery range, it can go 175 miles. This is the SU7 Max. It's a little bit more money. The 0 to 60 is 1.98 seconds, which is kind of fundamentally crazy. It will break your neck. Formula One drivers, by the way, do neck exercises for that reason. Because it's like 7 Gs, boom. And so anyway, so 219 miles in 15 minutes. The cheap one costs like $30,000, but it's not importable in the US. Okay, it won't be for at least 2 or 3 years, maybe 4 or 5 years. The CEO of Ford Motor Company said that the SU7 was the best car he's ever driven in his life. And so he wants to catch up, and I hope he succeeds and passes up. What China did, BYD bought a Tesla, all the models. They took everything apart, and they told their engineers, we're going to make it better. It used to be a long time ago, we could have copied it. They could, and even the logo. But now they're saying we're going to make it better. And what's a little scary is that CATL, the manufacturer, supplies this, and also the BYDs. They're a couple $1 trillion market cap. Factor 3 below or 4 below NVIDIA, but it's significant. And with that market cap, what they did is they formed a battery research organization like the Bell Labs for batteries. And we don't know what they have behind the screen, but they're just selling what they know they compete with, but they got rolled up behind the screen, all sorts of good stuff, not only for EVs, but also utility scale as well. And so this is another thing that we've got to, it is possible. We're still very innovative people, but we need a little bit of inducement. It's not Chinese government subsidy, it's euphoric investors in China, just like it was in the solar space. Okay, so what's happening? Well, in California, as you get more and more solar, you have what's called the duck back problem. Why is it duck back? Because this kind of looks like a duck. This is the back of the duck. And so during noontime, from noon until 3 o'clock in 2023, you go into negative pricing, meaning you're going to pay someone to take your electricity, either that or you use it to warm up the earth. And you also want to get neighbors to export energy. This is what Germany's doing with their excess solar, but once everybody gets more and more renewables, you can't do that. So if you're a first mover, you can do that for a while. And so because of that, battery storage becomes essential. We have what we have in pump storage. And so battery storage is now grew from 500 megawatts in 2018 to 16 gigawatts in the fourth quarter of 2025, simply because the duck back problem made it good enough that it became viable. Now, another exciting thing is that if you get a battery that takes ambient air cooling, it can go, and again, these sodium batteries now are selling, they're a little bit expensive, but wait 10 years, down to $100 a kilowatt hour, ambient air cooling. You can put in a Tesla charge station, let's say 6 or 8 charge stations. You can get a battery pack, and it's easy to estimate how much it needs. You need 5 megawatts per charging, 300 kilowatt or 350 charging station, which will be the standard within 10 years. And then you can sip electricity at negative pricing, 3 or 4 hours. So you're buying electricity free, and you're going to sell it for 15, 20, 25 cents a kilowatt hour. So it's pure money. You don't even need government subsidy for this one. So I said, well, what do you need? Because why aren't people thinking about this? Because the prices are coming down. I mean, within 10 years, they will be, you know, payback time. And once you get payback time less than 6 years, you're thinking really seriously about this stuff. And what you need is a regulation. Because in California, when you're in a small battery, commercial, like 20 megawatt hours, you have to do the regulations of each municipality. We have a waiver for the governments of 200 megawatts that only one standard, and so you only negotiate with the state. So last week I wrote a letter to the head of the California Energy Commission saying, can we get a waiver for 20 megawatt batteries for charging stations? Because you look at the projections, when these EVs get to be $20,000 cars, and it costs much less to run than gasoline or diesel. And the charging, I told you the charging rates. For years, I said the goal would be to make a battery last longer than the human bladder. And so let me translate it. You drive 200 miles, you stop, you need a rest stop, you want to go to the bathroom. While you're discharging your car's charging. If it's 5 minutes, everybody's happy, especially the gasoline station. Because if it's 4 minutes, you're not gonna buy anything. They make much more money selling you junk and soda, magazines, beer or whatever, candy, than they do selling gasoline. Gasoline is razor thin. So it's maintenance in your car is much where the profit is. It's not in the selling of the car. And so 5 minutes is perfect. They don't want 10 minutes because you block other customers. So 5 minutes, you'll wander into the shop and buy stuff. I learned this from Shell. I was an advisor to Shell, and learned they make more money in their service stations from selling junk than they do in selling gasoline. Okay, so it's nice that you need to know stuff like this. Anyway, if you look at the projections, you will have enough battery storage just from EV chargers in California. You don't need virtually no additional utility scale storage. But it's better because it's distributed and it's more robust. And it will pay for itself. So we just need the regulation. Okay, and of course, you know, who's gonna fight the regulation? Well, the oil and gas companies, because the early adopters will buy, and they're rich enough to own garages and home charging and stuff like that. But most of the people around the world don't own garages or parking. So you want a service station model, but you don't want a service station model where you have to pipe in 20 or 10 megawatts because that costs real money. But 1 or 2 megawatts is about what you need for half a dozen. It's okay. You know, there are step-up changes in the cost of rewiring at a 10 megawatt level. So the identification, if you want to know about really problems to think about, just knowing stuff like this can focus the mind on what you want to think about. Okay, hydrogen. Okay, we have what's called gray hydrogen. That's natural gas, mostly methane. You convert it into hydrogen and you vent the CO2. In terms of greenhouse gases, you're not doing any better. It's just all deeply tied to the cost of natural gas. What about natural gas costs? They're going to remain low. Natural gas has always been a byproduct of oil exploration, but we know there's lots more natural gas than there is oil. Natural gas is the end product of the evolution of fossil fuel underground. You end up with natural gas, and there's much more natural gas than oil. Anyways, blue hydrogen, you capture the CO2, but you're still using natural gas. You poke holes in the ground, you lose 1 or 2% leak out, then there's leaks out in the distribution, and hydrogen is very leaky, and there's no spectroscopic signature for hydrogen. Symmetric molecule, you're a chemist, okay? So, that's a problem, because it was only with remote sensing that we knew how bad the natural gas problem was. It was surprisingly more than the oil and gas companies were telling us. And until you have remote sensing, you can't do this. Remote sensing is possible, but you can put it on a drone. And you can have sniffers, and mass spec and a chemical signature, so hydrogen lands on and then you can discharge the hydrogen. And so you can have a drone going up and down pipelines, but until you have pipelines, the distribution is not there. It's shipped around in steel tanks. Green hydrogen is electrolysis, precious metals, things like that. But having said that, there will be a place for hydrogen in the new economy. You can use it as a reducing agent for steels. It's now being commercially used as mostly to upgrade crude oil to higher value products like diesel, airplane fuel, and gasoline. But chemicals and fertilizers, precious metals is a big issue. There are some ways. I've got one person working half-time. We think we can get the oxygen evolution reaction to not use precious metals really cheap, but we'll see. And then if that works, then we'll try to do the other. But again, hydrogen is leaky. There is a possibility that you can mine hydrogen. Because hydrogen is so leaky, you're unlikely to find large reservoirs in natural cap rock surroundings the way we do natural gas. So the mining is mostly, if you go into hot rock and you change the oxidation state of the iron in the rock, out pops hydrogen. And so, again, when I was inviting Shell, I stopped doing that, especially. It's very sad because they were putting 50% of their investments into transition and only 50% into the traditional investments in oil and gas exploration. So the financial analysts are forcing the European countries that are forward-looking to just go back and follow the US companies. They wouldn't look at hydrogen. They said, this is nah. And then 2 years ago, they went dark. Meaning they are looking at hydrogen. Because it's a technology, they should actually look at CO2 capture and storage because they know that technology is what. They know how to move fluids underground. And they know how to drill and they know how to do lots of stuff. So it's a possibility. The estimates for so-called white hydrogen are enormously low, 50 cents a kilogram. It's only because it's too new, so you have euphoric estimates. What it really turns out, I don't know, but it's a possibility. Let's talk about electricity demand and EVs. You've already heard about, and it will, when they get really inexpensive and